forget to like and subscribe this channel.
Now we will continue with the first part of lecture 2. So for the learning outcome, you should be able to explain the ideal or non-ideal behaviors of gases in terms of intermolecular forces and molecular volume. And you should be able to explain the conditions at which real gas approach the ideal behavior. So this is the comparison between ideal gas and real gas, which is also known as non-ideal gas. So for ideal gas, so we all know that between particles, there is actually intermolecular force between each of them. But for ideal gas, we will ignore the intermolecular forces that exist between each gas particle. And gaseous molecules are very small and they have negligible volume. So we assume that the volume of gas is actually the volume of container. We don't take into account the volume of the gas particle. So we will just make assumption that if we have 1 liter of container, so we will also have 1 liter of gas. So now let's go to real gas. For real gas, we take into account the intermolecular forces that exist between each gas particle. Therefore, the intermolecular force is significant or important because we consider the intermolecular force for the gas particles. And the gas molecules have a certain volume. Therefore, the volume of gas is not the volume of container for real gas. So how real gas will deviate from ideal behavior? So deviations from ideal behavior are more significant at high pressure and low temperature. It means that ideal gas can become real gas at these two conditions, which is high pressure and low temperature, because these two conditions will affect the intermolecular forces between the gas particles. And how is that? At high pressure, the volume of gas decreases, as we can see in this animation. So when the volume of gas decreases, the gas molecule here become closer to one another. So when they are closer to one another, therefore, the intermolecular force is important. So we cannot ignore the intermolecular force when the gas particles are close to each other. Therefore, the ideal gas is now become real gas. Now let's look at the second condition, which is low temperature. So how can low temperature makes ideal gas become real gas? So according to the kinetic molecular theory, temperature is directly proportional to the kinetic energy. So at low temperature, gas molecule possess very low kinetic energy. So the gas particle will move very slowly. So the kinetic energy of gas molecules can no longer overcome the intermolecular force. We cannot ignore the intermolecular force when the kinetic energy is very low. Therefore, the intermolecular force now becomes significant. We cannot ignore the intermolecular force. Therefore, ideal gas will become real gas. So how do gas approach ideal behavior? So all gases show ideal behavior at low pressure and high temperature. And why is that? So at low pressure, the volume of container increase. So the gas molecules are far apart from each other. Therefore, the intermolecular force can be neglected when the gas molecules are far from each other. Therefore, real gas will behave ideally.
At high temperature, since the kinetic energy is directly proportional to temperature, therefore, gas molecules will possess high kinetic energy. The kinetic energy of gas molecules can overcome the intermolecular forces, and therefore, the intermolecular forces cannot be ignored.
And therefore, real gas will behave ideally. So this is ideal gas equation, PV equals to nRT. And this is van der Waals equation, which is applied for real gas. So as we can see here, for ideal gas equation, the pressure is P, but for van der Waals equation, where IMF or intermolecular force becomes significant, the pressure is now P plus N squared A over V squared, while the volume in ideal gas is V, but for real gas, the volume is V minus NB. So the ideal gas equation is redesigned to describe the real gas behavior more accurately. So the van der Waals equation given here is actually correcting two parameters of gas, which is pressure, since we take into account the attractive forces between gas molecules, and the volume, since we take into account the volume of gas molecules. So the intermolecular forces between molecules for ideal gas is negligible since the molecules are far apart from each other. Therefore, the pressure in ideal gas will be greater because we ignore the IMF. But for real gas, since we take into account the intermolecular force, therefore the pressure exerted by the gas molecules onto the wall of container will be lower. So the pressure for real gas is lower compared to ideal gas. So P real is smaller than P ideal. So this is actually corrected by adding coefficient n squared A over V squared. So the pressure in ideal gas is equal to pressure of real gas plus n squared A over V squared. So n squared A over V squared is the corrections for molecular attractions intermolecular forces. So A is constant that indicates the strength of intermolecular force between gas molecules. So the higher the value of A, the stronger the intermolecular force for the gas. And the unit for A is atm, L squared mol negative 2. Now let's go to the volume of gas. So this is the volume of ideal gas, where the volume of gas is equal to the volume of container since we neglect the volume of each gas molecule. But for real gas, we consider the volume of the gas particle. So the gas molecule have certain volume. Therefore, the volume of real gas equals to the volume of container plus the volume of gas. Since volume of ideal gas is smaller than the volume of real gas, therefore the term volume needs to be deducted by coefficient NB. So V ideal equals to volume of real gas minus N times B. So what is NB? So NB is the correction for volume of molecules since we take into account the volume of gas particle in real gas. So N is the number of moles of gas, while B is constant that indicates the actual volume occupied by the gas molecules. So the greater the value of B, the larger the molecules or atoms for the gas. And this is the unit for B.